And after this, competitive wholesale electricity markets started to spring up all over the United States, but not in the Southeast. And we'll talk about this in a minute. Colored blue here are states that currently participate in competitive wholesale electricity markets. States that do this are said to be deregulated. Remember, we had the monopoly consensus from 1910 to 1970, and in that situation, we considered utilities to be regulated, meaning that they were making decisions in close coordination with state governments and utility commissions, and those utility commissions were regulating or fixing the price of electricity within states in a way that was fair, but also allowed utilities to cover their costs and earn a reasonable profit. So let's take a step back here. What do we mean by competitive wholesale markets for electricity? So competitive means that there's some sort of formal economic mechanism for deciding exactly which power plants should provide electricity, and that this decision is made on the basis of cost. So we already talked about what a wholesale market was, or at least who was participating, and that would be all these different entities that are circled. And so in a competitive wholesale market for electricity, the actual suppliers of electricity, that would be the monopoly utility and all the power plants that they own, or at least Monopoly Utility 1, and then all the power plants that Monopoly Utility 2 own, and all the power plants that the independent power producer own are pooled, which means they work together to meet demand. So every power plant that participates in the market is characterized in a couple different ways. And the first would be size. How much electricity can it produce in megawatts? And then also cost. How much does it cost on a dollar per megawatt hour basis to produce that electricity? And here we're probably not talking about the average cost of electricity or the levelized cost, but we're really talking about the marginal cost of electricity at that power. And so we can characterize every single power plant that's participating in the market in terms of its capacity, how much electricity it can produce in megawatts, and its cost in dollars per megawatt hour. And oftentimes the cost in dollars per megawatt hour is largely driven by the cost of buying fuel to produce the electricity. So in some cases, we have power plants that have costs that are almost close to zero. Examples would be hydroelectric dams and renewable energy producers. It's not that it costs nothing to build these facilities, but after you build the facilities, the cost of producing additional units of electricity is really close to zero because there are no fuel costs involved. Other types of power plants are extremely expensive. If you look all the way down at the bottom here, we see an oil power plant, a combustion turbine, so basically a jet engine that's using oil as its main fuel source, and oil is really expensive. And so what we can do is we can actually arrange all of these power plants in what we would call merit order. In other words, from least expensive to most expensive. And that's what I've done here. So at the very top, we have the least expensive types of electricity, at least in terms of their fuel costs. And then at the very bottom, we have the most expensive. And so the other thing that we want to do here is track the cumulative capacity that the total system could produce. Cumulative capacity is just as we go line by line, how much from that line all the way up could the system produce. So the first line, the cumulative capacity, is just the capacity of that first power plant, Hydro 1, so some sort of hydroelectric dam that can produce 1,500 megawatts. Then we go to the second line, we have some sort of large-scale solar farm that can produce 800 megawatts of electricity. So the cumulative capacity of the Hydro 1 and Solar 1 would be just the sum of their individual capacities. So 1,500 plus 800 gives you 2,300. We go to the next line, we have a nuclear power plant, which can produce 2,800 megawatts of electricity. So the cumulative capacity of all three that we've looked at so far, Hydro 1, Solar 1, and Nuclear 1, is now 5,100 megawatts. And we can go all the way down that last column and track the cumulative capacities. So now we can keep track of two things side by side: the cumulative capacity that the power system can produce, and at each level of cumulative capacity, what the most expensive type of generation would be. And so we can plot this information. On the x-axis here, we have cumulative quantity of electricity supplied for that exact same table. And on the y-axis, we have cost, or we're going to actually refer to it as price now, dollar per megawatt hour price. And so all the really cheap stuff is over to the left, the hydro and solar, and then nuclear and coal, and all the really expensive stuff is all the way to the right. That's oil. So another way of describing this exact same information is it's the system supply curve. So we're starting to sort of work our way back into a microeconomic context to try to figure out what the market price of electricity is. So the system supply curve is really just made up of this relationship between cumulative quantity supplied of electricity in megawatts per and in megawatt hours and the prices or the marginal cost associated with each source of electricity, each individual power plant that makes up that system supply curve. So we have a supply curve. All we need now to generate electricity prices or simulate them is some source of demand. So who makes up the demand in this case? It's us. It's the demand, the retail customers that are buying electricity from those monopoly utilities are the source of the demand. But in the same way that we were pooling different sources of generation or supply together to help meet electricity demand, we're also aggregating demand for electricity across all of the different participating utilities. And so that demand in any given hour is this, we treat it as this perfectly inelastic vertical demand curve. And so if electricity demand in this given hour is on the order of 14,000 megawatt hours, we put a perfectly inelastic vertical demand curve right at that point, 14,000 megawatt hours on the x-axis, and that generates an intersection between supply and demand. And so we remember from the microeconomic review that market equilibrium occurs at the point of this intersection. So we can calculate the market price of electricity as the value on the y-axis that is associated with the intersection between demand and supply. In this case, we get a market price of about $40 per megawatt hour. So what happens in a market, competitive market for electricity, if you happen to be a power plant that is to the right of this intersection, right? You might be a really expensive natural gas plant or an oil plant. Remember, when we put all those power plants in merit order, in order of increasing cost, we had all the solar and hydropower that was really cheap. It was all the way to the left in the system supply curve, and there was all the expensive stuff over to the right. Well, if the demand for electricity is only 14,000 megawatt hours, then all the power plants that are located in the system supply curve to the left of that get selected to run. If you are a power plant that's to the right of that, implying that you are more expensive, then you don't get to sell electricity. So what if demand goes up? Remember, we talked about how demand for electricity goes up up and down all the time on an hourly basis, based on economic activity, but also heating and cooling demands for people. And so let's say demand increases in a peak hour to well above 20,000 megawatt hours. And so now the intersection between supply and demand occurs at a much higher point on the y-axis, and we say now market prices have increased from $40 per megawatt hour in an off-peak period to $80 per megawatt hour in a peak period. And in order to meet that electricity demand, we have to use a much larger portion of the system supply curve. So a lot of those power plants that were not competitive in an off-peak hour and were not able to sell electricity are being able to sell electricity in a peak hour. But we still have some power plants that are part of the system supply curve that are to the right of the intersection of supply and demand. And those power plants are still not being used. Now, you might ask yourself, does that mean that we don't need those power plants? Well, that's complicated, and we're going to talk about that probably in the next class when we talk about long-term system planning. It has to do with, this decision of how much is too much generation to have in a system. And there are different ways of calculating that, and we're going to get into it. So actual wholesale prices go up and down all the time, right? We don't see that as retail consumers, but in the wholesale market for electricity, as demand is going up and down throughout the day, for economic reason, because of economic activity, but also because of heating and cooling demands, electricity prices are going up and down all the time. And so this just shows about 168 hours or 1 week of electricity prices in California from summer 2010. And knowing what you know about California and human behavior, we can sort of guess which times of day might be associated with higher electricity demand and therefore higher prices. Middle part of the afternoon would be associated with much greater air conditioning usage and higher electricity demand. And so those prices are higher. And then in the middle of the night, when people are asleep and they're not using their air conditioner, electricity demand goes down and the wholesale price for electricity goes down. So besides having competitive wholesale electricity markets, what are some other characteristics of utilities operating in deregulated electricity markets? So let's go through that. So one of the main characteristics of a deregulated electricity market is what's called vertical disintegration. So it's kind of the opposite of the concept of vertical integration, where one company owns different levels and stages of a business or a supply chain. So in the case of monopoly utilities, that sort of vertical integration was generation, the production of electricity, high voltage transmission, the way we would get electricity from where it was produced to the general area where it was to be consumed, and then retail distribution. So ramping that electricity down in voltage and delivering it to end use customers and interacting with customers. So vertical disintegration of the electric power industry in deregulated markets means that the old monopoly utilities now were no longer monopolies, right? They had to separate generation, transmission, and retail distribution into separate businesses. And specifically in the case of the generation assets, they were now forced to compete in wholesale markets in order to sell electricity. So in competitive electricity markets, generators, many of which used to be owned by monopoly utilities, are now competing with the generators that are owned by other utilities that used to be monopolies. And they're competing with each other on the basis of cost in order to sell electricity to retail distribution companies, and only the cheapest generators are selected to run. So a wholesale market is a collection of suppliers of electricity that are owned by, in some cases, companies that used to be monopoly utilities. They might be owned by independent power producers, and all of those different power plants can be organized in merit order into a red system supply curve shown here. And those are the entities that are competing against each other based on cost. We talked about how if demand is low, only a few of those power plants, only the cheapest ones, will get to produce, and a lot of those other power plants might get left out. There might not be a need for the in the market for electricity from those power plants. If demand goes up, a greater share of the power plants would get to sell electricity, but you still might have some power plants that are too expensive to sell electricity into the wholesale market very often. So that's the supply curve. Demand for electricity in the wholesale market, this perfectly vertically inelastic demand curve, is demand from retail distribution companies, right? So those retail distribution companies are buying electricity from the wholesale market, and the price that retail distribution companies are paying for the electricity that they buy from the wholesale market is is the wholesale market price. That is the intersection between the system supply curve and the demand curve. And again, that price goes up and down every hour of the day. So that electricity that retail distribution companies buy from the wholesale market that's produced by the generators that are competing with each other goes to us. It goes to the retail customers that are still buying electricity from those distribution companies. So this is you and me, etc. And in another state, there might be another retail distribution company that's selling to your uncle and your grandma, etc. So there is still a role for utility commissions. The utility commissions still have to okay the prices that retail distribution companies sell electricity at to their retail customers. Now, retail prices should always, in theory, be higher than wholesale prices because they include both the market price of electricity in the wholesale market plus associated costs with maintaining transmission and distribution systems. So I realize this is confusing and we are going to stick with it. And I think by the end of the semester, you will have a much more sophisticated understanding of the complexities of wholesale electricity markets than 99% of the people that you will interact with. And that will give you a great ability, I think, to understand the sort of costs and benefits of that system and what the unique characteristics of competitive wholesale electricity markets mean for different producers of electricity, especially renewable energy producers, as well as stakeholders like, retail distribution companies, the utilities that we read about in the newspaper. So today, most of the electricity that is bought and sold in the United States starts out in a competitive wholesale market. The states that are shown in blue here are said to be deregulated. These are states where retail distribution companies are buying electricity on behalf of retail customers in competitive markets for electricity, and the generators that are producing the electricity are competing with one another in competitive markets for electricity. Now, I mentioned to you, and what this map clearly shows is that we do not have competitive wholesale markets for electricity in North Carolina. North Carolina is not said to be deregulated. So that begs the question, why aren't all states deregulated? Isn't competition a good thing? Well, the U.S. never compelled utilities to join wholesale markets for electricity. All they really did was create all the frameworks necessary to encourage competition and allow for additional market players and to prohibit utilities from controlling transmission systems in a way that would preclude the buying and selling and trading of electricity over larger geographical areas. The reason why some states became deregulated and forced those power plants to compete with each other in wholesale markets is because they were under pressure from customers to reduce costs. And that pressure largely was a result of high electricity prices. So if you take a look at where electricity prices are the highest, it tends to be in states that are deregulated, that have competitive markets for electricity. And this is not to imply that competition increases the price of electricity. What it does suggest is that states that have higher prices for electricity are looking for ways to reduce those prices. And one of the common ways of doing that is to try to subject power plants to greater competition. We can also take a look at how retail prices for electricity for customers in deregulated states versus regulated states have changed over the last 20 years or so. What we might expect is that the states that were deregulated in the early 2000s experienced some leveling off or decrease in prices as power plants are subjected to competition, but we do not see that. The difference between the price of electricity in deregulated states and regulated states has mostly stayed the same over this time period, with the price in deregulated states being higher. What this suggests is that there are other causes for electricity prices being high in a state and increasing over time. And those could be access to fuel prices, the age of infrastructure, things of that nature. So the question is, did electricity market deregulation, this influx of competition, actually accomplish its goal of reducing prices for customers? It doesn't look like it. But that doesn't mean that wholesale markets are not important, because they do increase competition among power plants. And that has been extremely important for the growth of renewables in recent years, as well as the plight of nuclear and coal, etc. And these are issues that we're going to talk about a lot over the next several weeks. Okay, that's it for today. Next time, we are going to go inside an electric utility to learn about long-term system planning and the challenges of doing that. We have a reading for next time, and homework 3 has been assigned. So see you then.